So far we have looked at three iterative sorting algorithms, namely insertion sort, selection sort, and bubble sort. And all three of these algorithms were analyzed, and we saw that they run in time theta of n square. Their worst case complexity is theta of n square, and their average case complexity is also theta of n square. We are now going to consider a recursive algorithm called merge sort, and this algorithm is based on a design strategy which we call as divide and conquer. So firstly, merge sort is a recursive algorithm as opposed to an iterative one. And secondly, it's slightly more complicated than the brute force algorithms that we've been seeing for sorting. The design strategy that we are going to use, called divide and conquer, will be taken up in far more detail later on separately. For the purpose of understanding merge sort, I'll just describe the strategy very briefly. When you have a problem of size n, one way to design an algorithm for that problem is to split the problem into multiple subproblems. So let's say you split the problem of size n into two subproblems of size n by 2 each. This is the divide step. Then once you have divided the problem into these subproblems, you solve each subproblem. And having solved each of the subproblems, you combine the solutions to the subproblems to arrive at the overall solution to the larger problem of size n. So that's called the divide and conquer design strategy. So in this case, we need to sort an array of size n, and so by using the divide and conquer strategy, we will be first dividing the problem into two subproblems of size n by 2 each. And we'll do that by dividing the original array into two halves. The indices of the first half span from 1 to n by 2, and the indices of the second half span from n by 2 plus 1 to n. We're going to make a convenient assumption here that n is a power of 2. That will help us to uh, do the calculations much more easily. So in particular, we will, in this particular step, we are going to have equal size subproblems because n by 2 is going to be an integer. Now, having divided the original problem into these two subproblems, in the conquer step, which is the second step, we are going to recursively sort these two smaller arrays. And having sorted the two smaller arrays, in the third step, we are going to combine the solutions to both these subproblems. We are going to merge the two sorted smaller arrays into a larger single sorted array. So this is how a divide and conquer strategy is going to look like in general. It's going to have three steps. In the first step, we will divide the problem into subproblems. In the second step, we will conquer the subproblems or solve the subproblems. And then in the third step, we will combine the solutions to the subproblems to arrive at the overall solution to the original problem. Here's the pseudocode for merge sort. So merge sort is a function that takes an array of size n and sorts it. So the way the code is written is, if the size of the array is more than 1, we execute these statements. If the size of the array is equal to 1, then we do nothing. Basically, we just exit directly. And that's because if the size of the array is 1, then we don't really need to do anything to sort that array. It's a trivial case. So we'll assume here that the size of the input array is more than 1, and more conveniently we're going to assume that it is a power of 2. These two lines correspond to the divide step. What we'll do is we will copy the first half of the input array into an array called B, which has a length of n by 2. So the first half of A is copied into an array B, and the second half of A is copied into an array called C. And then in the second step, we are going to conquer the two subproblems. We are going to recursively call this merge sort function on the two smaller arrays, B and C. And then in the third step, we are going to combine the solutions to the two subproblems. We are going to merge the arrays B and C to create the sorted array A.